Please begin.
This meeting is being recorded. All right, yeah, thank you guys for coming and attending this seminar. I'm just going to present some work of mine, joint work with Marcus Curie and Christina Samani on the questions about stability of the positive mass theorem. So most of the results so far have focused really on the Riemannian case of the positive mass theorem. But of course, general relativity is a dynamical theory. It's evolving, and so you're going to have to deal eventually with sort of how metrics are changing and evolving over time. And one way you could do this is by really trying to tackle the translation of these geometric measure theory techniques and these metric measure techniques that are applicable in the Riemannian setting, and try to move them over to the Minkowski setting, where your metric is not now a positive definite, right? It now has some other signature to it. And I think there is work being done in that direction. I desperately was Googling to try to get it for you guys, but now I didn't find it, but I thought I'd mention that there's definitely work in this area. And I think some people have sort of started working on Hausdorff dimension with respect to Minkowski metrics and all these things. So that's a nice viable path that you could try to take. And in some sense, it's a very interesting and a natural path. And I regret not being able to find that. I'm sure a bit better Googling would have found it. So maybe someone can jump in.
So what are you referring to?
There are these, I just sort of off the top of my head remembered that people are working on trying to establish these sort of geometric measure theory tools for Minkowski signature spaces, right? Where you can sort of talk about length spaces. I think Christina and someone was working on talking about a natural length for Minkowski things that would work well for intrinsic flat convergence. And then there's like a Hausdorff dimension that's coming up, I think. But I guess my point was that that's not what I'm going to be talking about in this presentation. But in some sense, that's also a very natural path to try to talk about the positive mass theorem and its stability in sort of the dynamical setting. Did that sort of answer? It's not. It's kind of a non-answer, but it's more of me begging forgiveness from the people who are working on that path. But of course, then there's another way that you can work on this, which is you work on initial data sets. And what this allows you to do is you get to keep all of your nice Riemannian theory. But what you have to include now is a second fundamental form. So you have to include a manifold M, a Riemannian metric G, and a second fundamental form K. And this complicates things pretty greatly. But you still have a positive mass theorem, which was first proven by Shane and Yao. So that basically says that if your initial data satisfies this dominant energy condition, where mu is sort of like the energy density, and J is the momentum density, and you have this nice inequality between the two, and your manifold is asymptotically flat, and your second fundamental form falls off at a nice rate as you tend towards infinity, then the mass of this object is going to be non-negative. And of course, as in the Riemannian case, you also get a rigidity statement. So if the mass is actually zero, then something special happens. But what's different from the Riemannian case, where if the mass is zero, then your metric had to be Euclidean. Here, there's a lot more wiggle room. So if the mass of your initial data set is zero, no longer are you required to be Euclidean space, but now your data set has to arise as a graph in Minkowski space. So you have, your second fundamental form K is really just going to be the second fundamental form of a surface embedded in Minkowski space as a graph. And of course, that means that there's quite a few initial data sets that have zero mass. And this is going to really complicate a little bit the almost rigidity statement, because now instead of having one specific limit space that you know you're working towards, now you could have a whole family and a very large family of limit spaces, all basically these graphs in Minkowski space. So let's first
maybe maybe it would be good if you could, for those in the audience that are not familiar with the whole problem of the stability or almost rigidity, things to explain what the problem is, or maybe you're about to.
I'm gonna head back to the Riemannian case to sort of explain what the whole rigidity is, to get a clearer sense of what might be the rigidity in this more complicated setting.
Okay, thanks.
So sorry, yeah. So let's for the moment forget about the second fundamental form K, and instead let's work only in the Riemannian setting. So in this case, what you have is you have the Shane-Yao positive mass theorem, which says that if you have a scalar curvature, which is non-negative, and you have an asymptotically flat manifold, then your ADM mass is non-negative. And in particular, if the mass is zero, then there's really only one space that you could have been, which is Euclidean space. And so the natural question to ask, to move on from that statement to sort of generalize it, is to ask, well, okay, instead of when the mass is exactly equal to zero, what can we say for a sequence of these manifolds whose mass tends towards zero? Does a sequence have to converge to Euclidean space in some sense? And it was conjectured by Dan Lee and Christina Sormani that, yeah, there is a form of convergence. In particular, if you have a sequence of asymptotically flat Riemannian manifolds with non-negative scalar curvature, whose ADM masses are tending towards zero, and which don't have any interior horizons, which is, I'll talk about why that's an important condition later, then this sequence of Riemannian manifolds will converge in the volume-preserving intrinsic flat sense to Euclidean space. So there's a few things to talk about this sort of statements. First of all, let's get ourselves acquainted a little bit with what we mean by intrinsic flat convergence. Just sort of pictorially, we've sort of discussed it. I think Brian brought it up briefly in his talk. But the main idea is that when you are looking at these sort of sequences of manifolds whose masses are tending towards zero, certain pathologies can arise. And the most pernicious of these pathologies is that while your mass may be getting smaller, it's getting denser in some sense. And so the result of that is that you get these very, very thin but deep gravity wells where the cross section is a small sphere, but the small sphere is being dragged out down a long, long tube. And what these sort of examples show is that you can't expect for a nicer convergence to hold. For example, if you were to look at these pictures, you can see how a gravity well might develop and elongate and keep on elongating. And what would happen in a more pointwise convergence like the Gromov-Hausdorff convergence is that either you would end up with a a plane with a line attached to it, or you wouldn't have any convergence at all, because the well that's forming just becomes longer and longer and longer and longer. And that's not even the worst that can happen. You're not limited to one well. There could be a bunch of wells. And so there's all these sort of, this pathology can be really quite ugly if you are forcing yourself to have a very pointwise convergence, like the Gromov-Hausdorff convergence. And so instead, it might be beneficial to loosen it a little bit and sort of allow a more integral, or a fuzzier notion of convergence. And that's one such one is this notion of intrinsic flat convergence, which will, when these thin deep wells form, what basically happens is that intrinsic flat convergence will ignore them. They will disappear. And instead of being left with a flat plane and, say, a line attached to it, now you are just left with Euclidean space. So it seems to have, in this sort of setting, it seems to have that advantage. So now, why do we have this condition where you don't have any horizons, you don't have any minimal surfaces in your in any of your data sets, right? You're only looking outside of the minimal surface. Well, you can immediately see that if you are allowed to go beyond the horizon, that if you just look at the case of the short shield, you're also not going to get convergence to Euclidean space. In fact, you're going to get convergence to some kind of double cover of Euclidean case, right? Where you have two sort of planes forming, and they're connected by this very thin, very small tunnel. And okay, in that case, it's not so bad. You could probably say, all right, it's just a double cover, it's not too bad. But in fact, this is not the only thing that can go wrong with minimal surfaces. Minimal surfaces can also hide bubbling that the ADM mass won't see. So in the next example, all of these manifolds are, they all have non-negative scalar curvature, they all have small mass, but there's sort of this large spherical region attached to them. And so that also in no sense will converge to Euclidean space. So there's really, there's two reasons why you always want to work outside of minimal surfaces. And the first is because you think of the short shield example, you'll have this sort of double covering effect that you don't want. And the more important and more pernicious thing that you want to get rid of is this bubbling, where you have these large regions that are hidden behind the minimal surface or horizon that the mass can't see. And so you have no hope of controlling their convergence with the ADM mass tending towards zero. So you have to sort of find a way to cut these out. Okay, so still staying in the Riemannian case, what does the almost rigidity conjecture look like? Well, remember we have to avoid these two things. We first have to stay outside of the minimal surfaces. So we're going to immediately assume that in our family of Riemannian manifolds, they have no minimal surfaces except for maybe their boundary is a minimal surface. No, sorry, excuse me. No, closed embedded minimal surfaces, I should say, except for possibly their boundary. And the second thing we really want to avoid are these thin, deep wells. We don't mind the thinness of the well, but if the well is allowed to go on forever and extend infinitely far, that's a bit of an issue. So we need to find some way of making sure that when we are looking at convergence, we never are forced to look too deep down any particular gravity well. And one way to do this is to pick an anchor surface. So here in blue, this anchor surface is denoted by sigma A, And what it's going to be is just some sphere that you found, a nice region, a nice embedded a manifold inside, some surface, and you're going to look at a tubular neighborhood around it of some distance d. And what this does is, because you're looking at a tubular neighborhood, you're sort of fixing the distance away from the surface that you're allowed to travel. So you're anchoring yourself to reality, and this allows you to avoid going down any deep holes. And so the precise conjecture that Dan Lee and Cristina Sormani make is you fix an area A and some length d that you're willing to go away from your anchor surface, and you form this tubular neighborhood around a nice a round region. Either you can find a nice round region in the asymptotically flat end if you go far enough out, or you have some other nice way of finding it. So for example, in a rotationally symmetric spacetime, you have a bunch of nice round regions to choose from. And then you look at the tubular neighborhood around that region. And especially in the case of rotational symmetry, you can really focus just on the region inside, right? Your nice round surface sigma A should have an outside and an inside. And you don't really need to focus on what happens outside, because that's quote unquote in the asymptotically flat end. You just need to focus on what happens inside. So you have your round region, you have your tubular neighborhood, but you only really care about going in. With this setup, this region, the conjecture says that as a mass tends towards zero, a region such as this will volume intrinsically flat converge to a ball of a radius in a ball in Euclidean space with radius such that the boundary of that ball has the same area as the anchor surface that you chose in the beginning. So just to see, oh yeah, and of course I should mention that this is a bit of an old list. It should be updated, but there have been some progress towards the solution of this result. And what I forgot to add is, of course, Dimitri and Marcus and Dan have also established a stronger version of this result under the assumption that the Ricci curvature of your sequences are all bounded below. And actually, that's something I want to talk about more later when I have finished introducing sort of this how one talks about the stability for space-time positive mass theorem.
Okay, that's a question.
Yeah, please.
So you're talking about kind of like you're specifying a particular region. You fix an anchor surface and you go a certain, distance away from it, and the conjecture is that's supposed to converge to a ball. Is this the same as like a pointed convergence, or
yes?
Or why are we fixing an entire surface instead of a point?
It's similar to a pointed convergence. I think the reason why you are that's a good question actually. I hadn't fully thought about why not pointed.
I mean, it seems like maybe this is a stronger statement than just pointed convergence.
Yeah, that's true.
Kind of interesting.
I think the So the pointed convergence, you could fall down the well still, right? You'd have to somehow figure out, right, your points that you're working with. They could be further and further down any given well. And so you would still maybe not get some nice convergence. Does that make a little bit of sense?
Sure.
Like,
yeah.
So you need some way of really staying outside of a well, and an effective way of doing that is by having this very large region that can't possibly be swallowed up by these tiny little wells.
May I interrupt?
Huh?
May I interrupt?
Please, yes.
Yeah, I mean, it's right what you're saying, but then in Huang Li and Sormani, they choose the points in a way so they are far away from the well. So it's basically like what you are doing, they are actually fixing a hypersurface, and in that hypersurface, they can choose any sequence of points as the points that you want for your pointed convergence.
Right, but you still fix the hypersurface in order to
Yes.
stay outside of the well.
Yeah, yeah.
Yeah. So to answer you, Dimitri, I guess it sounds like you can do a pointed convergence, but you just need to make sure, as Raquel points out, that whatever you do, you really don't want to fall down these wells, because that will spoil whatever convergence you're trying to prove.
Thanks.
Yeah, no worries. Okay, so just to give us, I've written some things in nice, pretty colors, but let's get a little sense of what these actually might look like in an example. So here we can see the different regions. I probably should have made this more exaggerated, but your anchor surface is sort of at the top of that purplish region, and you're allowed to go a distance d up and below it, and then this region omega A is everything inside of your surface, and that little tip of blue right at the bottom, I should have drawn that much more exaggerated, because that's the part that you don't want to fall into. That part can go infinitely far away, but the constraints of working on a frame, anyway, you can use your imagination to pretend that little blue tip at the bottom is actually very, very long, and spoiling any sort of hope of convergence. Okay, so let's now that we have sort of this basic idea of what almost rigidity would look like in the Riemannian case, we need to now go back to the space-time case. So just to recall the rigidity theorem, if for your initial data set has 0 ADM mass, then your initial data set actually arises from an embedding as a graph into Minkowski space. And of course, there are a lot of embeddings of Euclidean space into Minkowski space as a graph, right? You just pick you pick your favorite function that isn't your favorite Lipschitz 1 function, and you can manage it. And this will give you some sort of very possibly rough initial data that has 0 mass. So there's a whole large family of it, which basically says that one has to rethink a little bit what you mean by convergence. But there is a way out, and the way out is precisely the idea that, well, okay, if you are embedding as a graph, then you need some base manifold, and that base manifold might be what converges. So I'll read you this long, or you can read this long explanation, but essentially, if you have a sequence of initial data sets, which are uniformly asymptotically flat with the appropriate decay on their second fundamental forms, all satisfying the dominant energy condition, and which have no interior horizons except for maybe at their boundaries, whose masses are tending to 0, then one can embed these manifolds as graphs in themselves, right? As R cross themselves, and then these with a different metric on the base manifold than the metric that you began with, and this base manifold with its with the Minkowski signature metric on R cross MJ, that will converge to Minkowski space. So basically what you're doing is, as your sequence is tending has their mass tending towards 0, you're saying, okay, let's remove the graph part of that sequence as best as we can and try to study what's happening at the quote unquote base part of it. So if you can kind of separate the metric Gj into its graph and its base, then what should happen is that the base manifold should converge to the to Euclidean space, and then you should have that the graph, you should be able to recover the graph as from your base manifold, and the second fundamental form should be arising as a second fundamental form of a graph. Sorry, so yeah, it's a bit, the wording is a bit confusing, my apologies. But the main idea is that in some sense, the sequence of initial data should become more and more like a graph into some Minkowski space. So the question is, how does one actually achieve this, right? How do you separate the initial data into its graph part and its sort of the rest? And the main trick to this is that actually there's quite a well-established way of going from initial data in the general to sort of this modified initial data, which is Zhang's equation. So you try to solve this second order PDE, and when you solve it and for F, what you are really doing is you're sort of saying, okay, how close can we write, how close can we get to writing our original metric G as the graph of another metric in Minkowski space? So for example, it might help to sort of picture what's happening in the Schwarzschild case. So above you have in the blue metric, the blue manifold. That's your nice traditional Schwarzschild, and can't really write it as a graph in Minkowski space. But you can, sorry, because it doesn't have zero mass, of course. But you can write it as the graph over another function, which is another space, which is the manifold in the purple manifold. And you can see that something sort of funky is happening at the minimal surface. So the two look quite similar up until you approach the minimal surface. But then the base manifold, this G bar, develops this infinite cylindrical end. It becomes just this cylinder right at the horizon for the Schwarzschild. And you can sort of see why that needs to happen. For in one case, you have to get this minimal surface. And the way you get a minimal surface in a graph, you have to become basically vertical. But of course, because we're working in a Minkowski space-time, the more vertical you're getting, your distances are getting smaller. So where on the one hand, you have to get this verticality from the purple manifold, that's not actually going to translate into an infinitely long cylinder in the original, because you're embedding as a graph in Minkowski, so distances are actually getting smaller and smaller and smaller as you are going down that end. Okay, so the first step in separating in proving this sort of rigidity for almost rigidity for the spacetime positive mass theorem is to solve this Jang equation and express your original metric G in terms of a function and this base metric. And then once you've done this, you can begin to sort of separate out your analysis into two pieces. The first piece that you're going to do your analysis on is sort of these G bar metrics, which you arrived at by solving the Jang's equation. And then the second piece of analysis that you want to do is sort of how does that translate to control over the second fundamental form, that is control over K.
Can you go back here a second?
Yeah, of course.
So the G here is some metric that you're going to try to write the G bar as a graph over?
No, so the G is the metric that you've begun with. It's one of your it's one of the members of your family, right? So you have, your initial data is a manifold, a Riemannian metric, and a second fundamental form.
Okay, so that's the GJ you're saying.
Yeah, that's the GJ. And then you want to sort of split it up into its graph part and its base part. And so G bar is sort of the base. I know it's kind of a weird way of, right, because you'd expect it in the left-hand side of the purple bit, right? It's basically the opposite. It's saying that G bar is a graph over G. But if you're thinking from a Minkowski perspective, it's the other way around.
Okay.
Yeah, it's a bit it's a matter of perspective, but the way that we're looking at it now is that G is a graph over G bar into Minkowski space, and with a Minkowski signature. Okay. Did you?
Yeah, that's good. Thanks.
So yeah, we were splitting this up into two pieces. We want to analyze G bar, and we want to analyze the second fundamental form, which we'll do later. So let's first start with G bar. And in general, the original reason for doing this Jang perturbation or this Jang equation is to turn your initial data into a more familiar setting in the Riemannian sense, in that your new metric G bar is going to have a scalar curvature which is basically non-negative. It's non-negative up to a divergence term. And so you can kind of see, okay, well, if our G bar, it has scalar curvature non-negative up to the divergence term, we're almost back into the Riemannian case of the positive mass theorem. So we can almost start relying on our previous tools that we have developed. But of course, we have to take care of this divergence term. So one way of doing this is you can you can conformally change this G bar metric once more to a G tilde metric, which is scalar flats. And you can even show that this G tilde metric will have mass less than, sorry, I forgot a very important part. When you do this Jang perturbation, the results has mass less than what you started with. And then this happens once more when you do the conformal change. You also get a further, you get another metric whose mass was less than what you began with. So if the mass of your original sequence tends to 0, then the masses of these perturbed sequences will also tend to 0. So once you have solved, you've moved now not only from G to G bar, but now by a conformal change, you move from G bar to G tilde. We're now in this completely Riemannian setting that we were hoping to be in. And this, all of what we've done so far is completely general. So if you were to have already the almost rigidity of the positive mass theorem in the Riemannian case, then you're very close to done, right? Because we've already now reduced a lot of our problem to the Riemannian case. But of course, you know, we're not there yet. There has been a lot of progress, but we're not quite done with the Riemannian case. So from here on out, it's all the calculations that I'm going to be making are specialized to rotational symmetry. I just wanted to point out that everything that's been done up until this point is extremely general and will still apply if you're hoping to prove an almost rigidity for the space-time positive mass theorem using the Riemannian positive mass theorem's almost rigidity. Okay, so now that we are really going to start leaning on the fact that we're in the spherically symmetric setting. And the first thing that we remember, which shows you just how restrictive spherical symmetry is that if you have complete spherically symmetric manifold with zero scalar curvature, well, you're really actually just Euclidean space. So what we've done is we've shown that you can move from a general spherically symmetric initial data set to this Jang perturbed data set J bar, which will still be spherically symmetric. And then you have one more step where you conformally change it. And after that last conformal change, what you're actually left with is Euclidean space. And so if under what you're actually really going to end up doing is just saying, okay, how do we unpack all of those changes and keep track of the masses, right? Because if you already have Euclidean space popping up in your analysis, you're probably pretty close to establishing the almost rigidity of the positive mass theorem. So the rest of the talk is really about how to unpack the fact that after these two perturbations, we ended up at Euclidean space. And that's going to involve two things. So, of course, we're going to have to control the conformal factor, right? Because that's the main difference. That's exactly right. You have the Jang metric, G bar, which is the base, and you want to show that that converges to Euclidean space. So that essentially comes down to establishing that the conformal factor tends towards 1 in some nice enough sense. And then the first thing that you can do is, well, what you always do is you multiply Jang's equation and you integrate by parts. And what you end up seeing is that you see that the mass actually controls this non-negative quantity. And in particular, it controls the gradient squared of U in terms of G bar. Once again, actually, this is also that last line right here. That's also completely general, and that's a point that I want to bring up at the very end as well. But now we're going to use the fact that G tilde is Euclidean space, and what you do is you now get a very strong control on the gradient square, the norm squared of the gradient of log of U in terms of a Euclidean metric and L2 in terms of the mass. And because we're dealing with rotational symmetry, the conformal factor is really going to be a function of only one variable. And so this this L2 control on its gradient is actually really, really powerful. It will translate into a C0 1/2 control on it and on large parts of the manifold. So what we're saying is that the logarithm of this conformal factor is going to tend towards 0 in the C0 1/2 norm as the mass tends towards zero. With a minor caveat, right? We've sort of, it's not over the whole manifold. We've now cut out a little bit of a section. And what this little section is it's sort of saying, okay, between you have in spherical symmetry, right? You can completely you foliate your space by these spheres, and you can categorize each sphere by its area. So you have some base area sphere that you're allowed to go to, and then you have some smaller fixed area sphere that you're allowed to go to. And then omega is sort of that region between them. And in that region, you have this extremely nice convergence of this conformal factor. But of course, outside that region, right, you should already have the sense that maybe things aren't going to go so well.
Wait, so could you go back 2 slides?
Yeah, this one.
Sorry. Yeah. So this is just maybe too unrelated, but can I ask why this quantity that you get after multiplying Jang's equation, integrating by parts, why does it look like exactly or very similar to like the stability, the quantity and the stability inequality for like a minimal surface?
Yeah, it's because you do something very similar to get it, right? You have your conformal. You're basically saying that your conformal Laplacian has positive first eigenvalue, and it's exactly the same thing that you would do when Shane and Yao are doing their dimensional reduction. I think it's sort of that. It's exactly that sort of nebulous of ideas, if that makes sense. It's yeah, it's exactly.
So why is the Jang equation like a? Well, I don't know what the comparison is. Should I think about the Jang equation as similar to a minimal surface equation, or should I think of it as a eigenvalue of conformal Laplacian equation?
No, it's more about minimal surfaces. I'm not. I don't want to claim to have full knowledge about why these two things are extremely similar. It has more to do with minimal surfaces. So that might be a more useful analogy, but it's exactly this. Yeah. Sorry, can you ask your question one more time? I sort of lost the train on that.
Isn't it also used for finding mots? That's the connection, right? To
yeah. Well, when you say it's used for finding mots, it's that statement follows from the fact that the Jang equation can only explode if in the presence of a mot. So any place where your solution f tends towards infinity, there must have been a mot in your original initial data set.
Okay, interesting. Thanks.
Yeah, there's also another interesting thing. I'll pull up the paper because there's quite a few interesting things that are cited in it at the end. But another interesting thing is the counter statement to that. I don't know is true. I do know that it's true in 3 dimensions. So if you have initial data set with a bunch of mots, you can construct in 3 dimensions. You can construct a Jang solution with blow up at each of those mots. But I don't know if that holds true in general. So you sort of it's not clear that it's an if and only if statement where the explosion of the Jang equation implies and is implied by the existence of a mot. Does that make sense?
Yeah, good. Thanks.
Anyways, good, sharp eye on the stability. I'm sorry I didn't have a better answer for you on that. But it's a very general question, and it speaks to maybe a technique for trying to solve these almost rigidity questions. Anyway, in this case that you, in spherical symmetry, as I said, you actually have a lot more power. You know that your conformal factor C0 1/2 converges to 1 in this sort of range of in this range inside of your manifold. So the main question now becomes, well, okay, how do we deal with that? And I'm very happy that Sajad is going to give a talk because what happens is you now not only are you're going to split your metrics into a base metric and the graph part, but now you're going to split the base metric that you have into a nice piece and a bad piece. And the nice piece is where you have all this beautiful control over your conformal factor and everything else. And the bad piece is hopefully going to be very small in size. And Sajad and Christina have come up with this machinery that allows you to do this with intrinsic flats, convergence. So given some conditions which are laid out here, they're sort of complicated, but the moral of the story is that if you have a large region which converges in a nice sense, so C0, or in our case, C0 1/2 to Euclidean space, and then you have a small region which is bounded by a small area hypersurface and contains a small amount of volume, then what happens is that intrinsic flat convergence will ignore that piece. So you don't actually have to worry about it. Sajad and Christina have your back. They can deal with it for you. So essentially, modulo this argument from them, you have the convergence of the base space to Euclidean space in terms of for this to Euclidean space in intrinsic flat sense as the mass tends to 0. And that follows in, yes?
Are you applying the smooth convergence away from singular sets to
Yes.
to GJ bar? The
Yes,
conformal metrics?
GJ bar, exactly. Because what's happening is this conformal factor is tending towards 1 very strongly away from these tiny little pieces of the manifold. So this, yeah.
And all you have on those tiny pieces is volume convergence?
Exactly, yeah.
And you don't have any control from below?
No, nothing. That's actually a really good point. In order to go from this like infinite cylinder to Euclidean space, you should already imagine that the conformal factor has to behave pretty nastily down those small tubes. And in fact, what happens is it tends to 0 exponentially quickly as you head down that smooth. Because what's happening is you're closing up this long thin cylinder and making it into a flat space. Yeah. Okay. Answered your question. I can't see your smiling face. Okay. All right. So I feel a little bad for skipping through this, but this is sort of some of the small details of what you need to do in order to apply Lorentzian and Sermani's work in order to cut out these bad regions. So let's, but it's very interesting and it's important, and you know, of course, it's you wouldn't get the convergence result without it. But I would like to talk a little bit about what happens with the second fundamental form, actually. So right before we were just talking, we were saying, okay, this base metric tends towards Euclidean space, and we forgot a little bit about the second fundamental form. So let's bring it back. Okay, so we have this nice proposition, and once again, actually, you're going to find yourself mirroring your argument that you had with the base space, right, where you had this nice Sajad Sermani, Lorentzian Sermani idea where you have smooth convergence away from a singular set. You're going to do the same exact thing for this difference between. Sorry, I should tell you what up here, H is the second fundamental form of your metric as a graph, and K is the second fundamental form that you were given when your metric was an initial data set, and you want to show that they are converging in the L2 sense to each other. And the idea is, well, okay, we're going to split it once more into a good piece and a bad piece. And the good piece is actually not too difficult. So we have this proposition where you see that outside of any fixed surface of a given area, outside of that, the L2 norms of the second fundamental form as a graph and the second fundamental form as an initial data are converging to each other and are bounded, in fact, by the mass. And let's just take a moment. That's actually, this might seem mysterious, but the proof is actually quite simple. If you go back a few slides, and my apologies, you look at this equation, and right there in the middle of it, you can see h minus k g bar squared dvj. The only problem is you have this factor of u squared. So wherever u squared is tending towards 1, then of course you're also going to get control over their differences, over the L2, the norm squared of their distance to each other. So that's where this proposition comes from. And that's pretty general. So as long as you have good control over u in some region, then you also will get this nice control over the distances between the graph second fundamental form and the initial data second fundamental form. So as you can imagine, actually, it's a little bit more difficult to estimate h minus k on the inside. And by inside, I mean inside the bad set, where we sort of are hoping to cut out. And this is because your conformal factor is decaying exponentially fast. And so you don't actually know a priori if the L2 norm of h minus k is going to be bounded even. But actually, it's possible to show in the spherically symmetric case that it will be bounded, with the assumption that the entire family had a bounded, in the L2 sense, initial data. So all of your k's, each kj has an L2 bound uniformly above by some fixed constant b. And then you do get this uniform L2 bound. And unfortunately, this is, this is another place where one has to lean very heavily on spherical symmetry. And the main, and I'll walk you through it to show you why, and maybe someone will see how to avoid spherical symmetry or see how to move beyond it. But the general idea is, well, we want to sort of go back to this first inequality that we had, where we could bound we want to bound, we're going to get something very similar where we had u squared, but instead of u squared, we want to pick a better test function, is the point. And so we can get this comparison here. That's still very general, in fact. And we'll see that, okay, if we pick our test function well, we can pretty easily and almost for free bound the norm squared of its gradient, because we get to pick the function. And so the real challenge is bounding the integral of the scalar curvature of g bar against b squared. And this is the point where you really need spherical symmetry. And the reason for that is in spherical symmetry, you have a very explicit and easy formula for the scalar curvature. And you can actually, it's an ODE in terms of your warping function. And And what you can do is you just integrate by parts. And after integrating by parts and realizing that which terms have some geometric content to them, you can obtain this equality here. So you see that the integral of a scalar curvature against this test function is precisely equal to the term on the right-hand side. And now if you look at this, you see, okay, the first term, the phi nabla phi, that you can bound by using the Cauchy-Schwarz inequality. And so really the only piece of this equation on the right-hand side that you really need to be worried about is the integral of phi squared times h bar squared. And so that's what we're going to try to bound. And of course, because we're picking phi to be between 0 and 1, we actually really only need to bound the integral of the mean curvature squared. And this is where we use some trickery. We change coordinates a lot. You change, you basically just change coordinates a few times. So first, you add and subtract the trace with respect to the surface of the second fundamental form k. And then that first term, when you have h bar squared minus the trace s bar k squared, if you change coordinates, then you see that actually that h bar squared has a factor of 1 plus your f, sorry, here, f is your Jang equation, and f sub s denotes a partial derivative in the variable s. So you see that your h bar is related to your original mean curvature of your level sets in your original metric g by this factor of 1 plus f partial derivative of f with respect to s. And then now you'll look in that first integrand, and what you actually get is that's precisely the Hawking mass, or what it's exactly the Hawking mass. And we know that the Hawking mass is non-negative because we have no minimal surfaces, and we have rotational symmetry. And then what's left over when you added it is actually bounded above by the norm of k squared. And so you have this term which is bounded by the Hawking mass plus a term which is bounded by the L2 norm of k. And so if we assumed that the L2 norm of k is bounded, which we did, then this whole object is bounded above. And then we've shown that you have that's in the bad set. You may not have convergence in the L2 sense, but at least it's uniformly bounded. But previously, what you showed was that the volume of that bad set is converging to 0. And so although you might not have L2 control or L2 convergence, you have LP convergence for any p less than 2 just by Holder's inequality. And so that sort of rounds out the argument there, which is to say that from the techniques that we use to prove the almost rigidity of the positive mass theorem in the Riemannian case, you can see that the G bar metrics converge to Euclidean space, whereas using some slightly different techniques for the second fundamental form, we see that the LP difference between the metric as a graph's second fundamental form and its initial data second fundamental form converges to 0. And with that, that's the end of the talk. And I'd really like to thank you for your patience and the opportunity to speak. And please.
Great, thank you.
Yeah. Oh yeah, I wanted to mention